plus 1, which is a solution to L plus NU, UN plus 1 equals UN. We don't like this operator. We've said this before. It's badly conditioned. It has all those eigenvalues, including the minus k that goes all the way to the next building there. Let us precondition with L inverse. And I emphasize again that it's not that we precondition, it's just an interpretation. We do the same calculation that we did before, and what we find is that we need to solve this equation. What is this equation? The right-hand side is a simple, a single implicit time step, as though there's no nonlinear term. And on the left-hand side, it's like taking a linearized time step, as we said before. This is exactly the same left-hand side as before. And you recall that conjugate gradient asks only that you be able to provide the action of an operator on a vector. Since you know how to take a time step, you know how to take a linearized time step, and hence you know what to tell by conjugate gradient to do. Now, the enhancement factor is going to be enormous. If lambda 1 is close to 0, then lambda 2 over lambda 1 is huge. You know, if you're looking for one that's about to bifurcate, and there's another one, well, he's close by, okay, but still, this is twice as much. And as you move forward, well, it's going to get closer and closer, and you can get, basically, you get an answer here in not 10,000 or 100,000 iterations, but 2 or 3 or 5. Because dividing by 0 is a very powerful operation. Multiplying by 1 is a very, very weak operation. Okay, so here are some eigenvalues okay, so here's an example of an eigenvalue calculation. Let's see, what should I do? No, maybe I should, there's somebody here who works on Bose-Einstein condensation, right? That's you? Okay, so let me give that example. So here's Bose-Einstein condensation. We've done lots of Navier-Stokes predicted by Bose in 1924 and Einstein in 25, and first realized experimentally in 1995. That's a long time to wait, but I guess they weren't around, either of them, when it was predicted, but they had many other honors, so it's not too bad. A Nobel Prize in 2001. The equation, and again, maybe you can answer this better than me, that describes that, just as Navier-Stokes describes fluids, the equation used for Bose-Einstein condensation is the Gross-Pitaevsky or nonlinear Schrodinger equation. I don't know if it has as high a status as Navier-Stokes does. Is this equation really considered to be the right equation, or is it just kind of an approximate way of thinking about it?
Just the approximation.
Sorry?
Just
an approximation, so it doesn't
Yeah.
have the same status as Navier-Stokes. So here is the equation to be solved. We want to find the eigenvalues. The eigenvalues and the energies determine the decay rate of the condensate, and you know what this means much better than I do. Again, I did the numerical calculations, but I know nothing about Bose-Einstein condensation. The solutions we're looking for are wave functions kind of like this. They're bumps. These are inside a trap. Again, you'll correct me if I'm wrong, but I think I'm using the right words here. For a Hamiltonian system, the equations, the eigenvalues are found in complex conjugate, not merely complex conjugate, they're plus and minus pairs. So the bifurcation, we didn't get to this in the yesterday in the Hamiltonian systems, but what happens in a Hamiltonian bifurcation is not that picture I was drawing here like this, but what happens, I think we saw it in Faraday case or another. What we see, the Hamiltonian bifurcation, since they have to occur in plus and minus pairs, is we have two that are on the imaginary axis, minding their own business, and then they come here at 0, and they go off here. They come down and go off here. And that is a Hamiltonian bifurcation. They have to stay plus and minus. I think we saw it in Bissett Faraday. So that's what I've drawn here, is what's happening at a bifurcation is some guys that are going on the axis. So again, these are the eigenvalues we want, they're the ones that are closest to 0, so we want to act with the inverse. The exponential would not be that helpful. I think this is supposed to be the exponential of that. I'm not sure. Okay, so the inverse is going to be very, very effective. What's going to be even more effective in this problem is taking the square. It's going to turn them real. Okay, if we take the square of this, we get this. These imaginary ones become negative, and then these real ones become positive. Okay. So we can do the steady state solving the same way we discussed. Is that the other thing? Okay, well, maybe I'll take this opportunity. I know we'll go over by 5 minutes. I don't think more than that. We do the steady state solving. What I didn't mention yesterday in Hamiltonian, for those who were here, is but I talked about it, I think, with you afterwards. I just talked now about Hamiltonian bifurcation. It looks like that. This is another Hamiltonian bifurcation. This is the collision of the two steady states that exist in Hamiltonian systems. You recall we said that steady states are saddles and centers, and that whole variety of steady states that we discussed for dissipative systems, the spirals and the nodes and the this and that, they don't exist. We only have saddles and centers. And here is a saddle and here is a center, and they are about to collapse, and they do. They collapse. You can see this loop here. It's connected by, this is a homoclinic orbit. It goes from, it sits here for an infinite amount of time, and then it goes and comes back and sits here for an infinite amount of time. This homoclinic orbit. And it's going to shrink and then disappear. And this is what the phase space looks like for a Hamiltonian saddle node bifurcation. This is what the function looks like. It used to have two maxima, and now it has only, it goes to a minimum state and then has only one, it has no maximum, I should say. It goes from two maxima, two extrema, to none. So these are what the results look like. There's a Hamiltonian saddle node bifurcation. These are two different cases. When the trap looked like, okay, this was all done. They've done the calculation already with spherical symmetry. Now they wanted to do it with cylindrical symmetry. So they had two traps that they called cigar-shaped, like this, and pancake-shaped. That's kind of like that. Words. Both are axisymmetric. One of them looks like a pancake, and the other one has two big axes and one small, and the other one has two small axes and one big. So there's the cigar and the pancake, and there's a saddle node bifurcation in each case, and we computed that with these methods. And so here's a summary of what I've said about those methods. Time stepping, I've recommended implicit and explicit Euler. Some of you will tell me if your communities recommend something different. Then I've written the notation here as I've defined this preconditioner I minus delta T L inverse, which is a Stokes operator or implicit steady state solving. You do by Newton's method, and instead of looking for the roots of n plus L, you look for the roots of B minus I, and that is an effective preconditioner, and that generally 3 or 4 Newton steps are all you need to converge. That's always the case. I mean, that has nothing to do with my methods. Generally, Newton's method works in 3 or 4 or 5 steps, or not at all. So it's very fast, it's very powerful, and so powerful that, like anything, it can explode. Right? And each one requires, each Newton step requires you to solve a linear system, and in my experience, I say 200 here, but since then I've done problems that required more like 2,000 but so you have an outer iteration, inner. Linear stability analysis, we use the power method, but with the inverse operation. Just as before, we're not using the inverse of nu plus L, but the inverse of nu plus L multiplied by L inverse, effectively. Just like Newton's method, the multiplying by the inverse is very, very powerful. It will work very quickly, or not at all. It will explode easily. And each one of these steps takes around 200 or 1,000 or something inner loops. And that means matrix vector products. And that's all I have to say.
Right, well, I'm here to close off. What's happened with the exam?
That I don't know. I haven't been told.